Let us discuss about the case potential step when energy of incoming particles are less than potential V naught. So when the energies are less than V naught, so you have many particles which are coming towards this potential with energy less than V naught. Classically, what should happen? Not a single particle should transmit. But quantum mechanically, some particles, even if their energy is less than the potential, some particles they will transmit. So let us see how quantum mechanics tells us. So this is region 1 for x less than 0, and this is region 2 for x greater than 0. So in region 1 for x less than 0, what is the Schrödinger equation? This is the Schrödinger equation. This can be easily written as, it is same as the previous case, no changes, it is exactly same as the previous one, plus k1 square psi is equals to 0. And exactly as in the previous case, we know its solution. So there is a plus sign here. Okay, to bring the plus sign, we have to take I in our exponentials. So general solution is e to the power I k1 x plus b e to the power minus I k1x. So no changes, but changes will occur when you look at region x less than 0. This will be different than the previous lecture, because when x is less than 0, no, this time the x is greater than 0, sorry. So when x is greater than 0, the v naught value is more than the e value. Okay, so v naught minus e is the positive quantity. Okay, remember v naught minus e is positive. Why I said this is because of this. Let's write this Schrödinger equation. So for x greater than 0, I take the wave function as psi 2. Okay, so e psi 2 is minus h cross square divided by 2m, the kinetic part of the Schrödinger equation, d square psi 2 divided by d x square, plus v naught psi 2. Now I cannot do one thing. I cannot take v naught this side and write everything as e minus v naught, because if I write e minus v naught, then it's a negative quantity. Now why this negative quantity will hurt us? Let me show you. Let's do the same thing that we did before. So what we did, we can write it as h cross square. So we are taking the h cross square divided by 2m towards the left hand side. So what do you get? We get this psi 2 divided by dx square. We get this, and what we have e minus v naught psi 2 equals 0. Okay, so what I'm trying to say is, I'm trying to show you the problem if you do this. Okay, let's see what is the problem that we will face. Plus 2m e minus v naught divided by h cross square psi 2. So you want to do this, right? Exactly that we did before. But the problem is when you try to define this as k2 square. So let's define it. Why we are writing in the form of k2 square? Because it will be a very beautiful oscillatory type equation which is easy to solve for us. So if you write k2 square as 2m e minus v naught divided by h cross square, then what is k2? K2 will become root over of this. So this is root over of a negative quantity. This is the problem, because e minus v naught is negative. So this analysis is not good. Okay, we don't know how to handle this. So what we do is we play a clever trick. The clever trick is we write it instead of E minus V naught, okay, and instead of this plus, okay. The clever trick is take a minus and write this as V naught minus E. Then what happens in the next step? This cancels and you have minus instead of E minus V naught. What do I have? Instead of E minus V naught, I will have V naught minus E. Now it's a positive quantity. So once I have here, I should have what? Here I should have V naught minus E. Now everything looks good because V naught minus E is a positive quantity. But the price we pay is this. We have a extra. We have an extra. The price we pay is we have an extra negative sign. This is the price that we pay. But now when you have a differential equation with a negative sign, see previously we had a differential equation with a positive sign. Look at here, it had a positive sign. But now what is the differential equation? It is d square psi 2 divided by dx square. Now there is a minus k2 square. See how things have changed here. Minus k2 square psi 2 is equals to 0. This is the equation. Now the general solution will not contain I. The general solution will only contain exponential. So let me show it. This is the general solution. You can see on the screen. This one. It now contains exponential without I. So here they have written k2 dash. It's not a big deal. The reason I have written k2 dash is to differentiate it from k2 that we used before. So what is the general solution of psi 2 now? It is c e to the power minus k2 dash x plus d e to the power plus k2 dash x. So now you have your psi 1. This is your psi 1. The psi 1 contains the incident and the reflected part. And now you have your psi 2. Here you have the entire psi 2. But you have to remember that this part will be 0. Okay. Yeah, you have to remember that there is a this is 0. Why this is 0? Because as x goes to infinity, this term will go very high and the psi 2 will blow up. And remember, our psi 2 has to be finite. Okay, that's why we have to cancel the second general solution. So only this term will remain. So now you have your psi 1 with 2 terms. You have your psi 2 with 1 term. Find the reflection transmission coefficient. Same step as before, and then you will get the following result. The interesting result is related to reflection coefficient. As I said before, if the energy is the important result is transmission coefficient. So since you see that the calculation of reflection coefficient gives us 1, the transmission coefficient is always 0, because we have already studied about reflection and transmission coefficient in electrodynamics, and we saw that reflection plus transmission coefficient is 1. But you would say, what is this stupidity? You just said that in quantum mechanics there will some particle which will penetrate the region, and now you are saying the transmission coefficient is 0. What is this? Yeah, it is because I am saying that the transmission will happen. Yes, it will happen, but it will not go to x is equal to plus infinity forever. It will go to certain region inside and it will come back. I mean, there will be 100% reflection because reflection coefficient is 1. There will be 0% transmission because transmission coefficient is 0. But if you look at the solution, this solution is exponential e to the power minus k2x. So it's an exponential decaying function. It means why there is e to the power minus k2 dash. Exponentially decaying function means as x increases, okay, this value of psi2 goes down. As x increases, value of psi2 goes down. So if the value of psi2 goes down, then the probability density to find particles psi2 will also go down. Okay, so they will enter the region. Classically they cannot enter the region, but quantum mechanically, since you are getting a decaying exponential function, it means these particles have entered the classically forbidden region, okay, but they come back. But the quantum mechanical phenomena is just related to the entry of particles in the classically forbidden region. This is the idea, that they at least enter. Okay,